Hello, good morning. I will first of all, I am not a Python core developer, I'm a Django core developer. I don't want to make that very clear. Python core is even more difficult than Django. But let's talk about, introduce me a little bit. So, as you've heard, I'm Andrew Godwin. I am perhaps most well known for working on Django. A long part of that time was doing Django migrations. I spent about 8 years battling MySQL and Postgres and SQLite to get those working. And then recently I've been working on channels and async in Django. In fact, about a week ago, I got the patch done for full async support in Django views. So that's very exciting and coming in the next version. But I'm not going to talk about Django too much today. I'm going to talk about some other things. In particular, my job at the moment is principal engineer at Eventbrite. And I want to talk about that particular word, engineer. I call myself an engineer. I have done for most of the time I've been working. My very first job had that in its title. But what does that mean? At least in English, engineer applies to pretty much everything mechanical, right? Like people who make airplanes, people who make bridges, people who make things in the real world. How do we relate to them? In particular, what is confusing is I went to university, and there I studied computer science, which is a different kind of thing. In fact, I almost didn't go to study that. I almost went to study physics. And I went to the university, I toured around it. It was Oxford, back in England. And the physics department was very lovely. I enjoyed my time there. It looked very difficult. I was like, this looks a bit hard. I went to the computer science department, and I was like, oh, this looks much more familiar. I already know programming. How hard can it be? I was unfortunately very mistaken. Programming is not computer science. Anyone who tells you that is perhaps not really aware of the differences. There is programming in computer science, that's true, but they're two quite different disciplines. And so I want to kind of talk through that journey for me and how I view things now, and then how it applies to how we develop software and how I still develop software. One of my favorite quotes is by Edgar Dijkstra. Dijkstra, for those who aren't aware, invented the basic modern graph traversal algorithm that your phone uses to find places when it's doing routes. I love this quote because it says something very simple. Computer science is no more about computers than astronomy is about telescopes. What he's trying to say here is that it's not really about the things you run the programs on. Computer science is this wonderful world of pure programs. The computers are almost an annoying distraction in some cases. One of the things I discovered at university was that computer science is quite what I would call idealistic in English. It's almost ignores the real world and goes beyond into the virtual world. It's one of the few places you can think about things in a purely abstract theoretical sense. There's a good reason at Oxford, computer science is part of the mathematics department. They're kind of the same thing. I didn't really appreciate mathematics when I was in school because it's all addition and subtraction and boring things like that. I got to university and was like, oh, mathematics is much more interesting. There's proof, there's logic, there's linear algebra, there's all these things they sort of, at least back in England, they just don't give you when you're a young child. And you get to university and realize that mathematics is totally different from the stuff you thought it was. There's no calculators really needed. And one of the things about computer science and its idealism is that we have this simple idea of what we can compute, what is possible. You may have heard the phrase Turing Complete. This refers to an idea put forth by the great Alan Turing of basically a theoretical computer. I'm not going to go into too much detail about that computer. It basically has some memory and a big infinite tape. The key thing is, it's a really silly design for a computer if you were to build it now. But the wonderful thing is, it's effectively the same as any other computer. If you can run it on a Turing machine, it's a full program. That means it is computable by any modern computer. You can reduce anything currently down to that one thing. You may have seen games like Minecraft, where people build whole computers in Minecraft. That's because Minecraft is, as a game, Turing Complete. It has enough memory and state that you can build arbitrary things in it. In theory, given enough time, you could build Minecraft in Minecraft. It just wouldn't run very well. It'd be very slow. And so computer science is this wonderful world of proving things are possible. There is part about speed, and that's important too, but it's mostly about taking a problem and showing, like, is it equivalent? Is it the same? Can we do this on a normal computer? Can we do this in what's called polynomial time? And that really appealed to me. The problem, though, is when you go in, like, the first 6 months are fantastic and idealistic, and then you try and write stuff. And as an example, I want to talk about sorting. Sorting or ordering things is one of the most popular problems in computer science. Everyone knows that it has to be done in a certain amount of time, which we say in O notation is O(n) log n. Now, O notation is fun because O notation completely ignores any actual, like, time factor. It's just a factor of how much it grows with the size of the list. And in the real world, it's maybe not as useful as it might seem. As an example, here I have a sorting function implemented entirely in Python sleep. You feed it a list of numbers. It launches that many different coroutines in Python. They all sleep for the right number of seconds. And at the end, you get a sorted list. There is no actual sorting involved, but it does still produce a sorted list. If you ask someone what kind of time factor this runs in, you get a wonderful puzzled look of, first of all, like, well, why are you doing this? Like, what's wrong with you? What's happening here? Then they study, they go, well, it's probably a length of the list. Eventually, you get someone, they come like, you can't really reason about this. Of course, you shouldn't do this. It's a ridiculous idea. If not only because it is still sorting, it's relying on Python's coroutine implementation, which sorts things numerically in time. But it's an interesting idea of, like, code is never quite the same in the real world as you'd want it to be. It's not quite as clean, shall we say. So, one of the other fun things, and the thing I truly love about computer science, is proof. If you've ever worked with logic systems or algebras, you will know this idea, like, you can have an idea, a conjecture, as we say in English, and you can take that and a set of rules, and you can work down and prove that what you have is correct. Now, this works for basic logic and basic ideas, but it also works for entire programs. My tutor at university, his department was basically about proving things were correct. They at one point had a Java compiler that could prove, given a few days, that a basic Java program was correct. Now, the problem here is Python is maybe not the best language for this. So here is a very simple program. I would like to prove, ideally, that this program is correct. Now, for that, I need a specification. My specification is it returns true for the number 2 and false for everything else. Now, you'd think that was simple. And indeed, if Python was a normal, reasonable language, this would be simple to prove. We could do it by what's called induction or a few other things or different things. However, Python is quite fun. You can do things like this in Python, where you can reassign true to false. And not only does true become false, but somehow true equals false is true, but I'm not sure if that's true or false. It's a very puzzling thing. Thankfully, Python 3 has fixed this. I can no longer scare new programmers at work with this particular problem, but it's still a fun you can still do things like this in Python 3 if you're in the C layer. Like, you can change what strings mean, you can change what integers are, it's very fun. And so Python isn't really the best language for proving things. We'll get to what it's good for later. But I want to show you, like, what do proof languages look like? And as many of you know, I work on asynchronous programs. Asynchronous programming is very, very difficult. It's just because concurrent programming is difficult. Threads, coroutines, separate processes, these are all difficult things to think about. One of the things that really helps me think about these things is a proof language called CSP. CSP looks ridiculous, I'll grant you, but what it's about is about proving how things run concurrently. It's a language for proving sequential things. In fact, CSP, the name means concurrent sequential processes. That's kind of where it came from. Using CSP, you can model things like a vending machine or basic states. You can prove if they deadlock or if they live lock. You can do all the basic reasoning about a distributed or concurrent machine. In fact, if you are doing a big kind of annoying piece of hardware or project, it's maybe not what you choose initially, but like you can sit down and model things in this. And because it's a proof language, it's an algebra, you can literally sit there and prove that the whole machine never deadlocks. Now, this is fair enough for a small definition. You try doing this on a giant code base, it's going to take you basically forever, but it's nice to have that option. But if you're talking about a real programming language that you can actually run things in, there is Haskell. Haskell is really interesting because not only is it a purely functional language, it also is kind of like Python. I learned Haskell after Python, hilariously, but it has list comprehensions, it has pattern matching, it has a lot of the things you're used to, but of course it's functional, so the actual basis is entirely different. This is a perfectly valid Haskell program, and the key thing about Haskell is its type system. Everything is very strongly typed, not only for the types of the values, but of the functions. And it's a functional language, so everything is a function. Like this itself is basically a way of saying, does this contain something? And it's implemented saying, well, if it's a nil list, it does not contain something. If it's a node, then we can go and recurse down and see if either side contains it. It's basically a tree implementation. But what's fun about Haskell is, once you've written the types, you've basically written most of the program. If you've ever written Haskell, you'll spend about 90% of the time writing your types perfectly. Haskell will then infer half your program from the types you've written, and then you finish off and write the other half, and you're done. It's kind of an amazing way of going at these problems. Now, this is great. I love Haskell. It's fantastic for doing things like sorting, things like basic algorithms, list finding, graph traversal, all the classic computer science problems. But there's one thing it's not very good at. Haskell assumes this perfect world where the real world doesn't exist. As soon as you try and talk to the outside world, try and do some I/O or some input or talk to a web server, it runs into a wall. It doesn't understand that the real world can exist. It does. There's a thing called Monads. I'm not going to try and explain Monads until the lecturers here would do a much better job than I would. But the point is, it's this weird leaky abstraction. You come against this wall, it's like, well, we have a way of thinking about the outside world, but it's basically just, it's a thing that can fail at any time. It's unreliable, it's not perfect in the same way. And that's kind of where computer science, in some ways, runs into a wall. It's really fantastic in theory. It's amazing for thinking and reasoning about how we talk about things as algorithms and abstract ideas. But when you come to actually write programs, it sometimes doesn't quite get there. And so that's where I think we get to the change from doing computer science to doing software engineering. This quote is very misattributed. The original quote is from Benjamin Brewster many, many years ago, but I particularly love it. In theory, there is no difference between theory and practice. In practice, there is. If you've ever written software, which I presume you all have at this point, you know this is very true. How many times have you sat down, you've written something, you've gone, great, it's perfect, let's go, you hit the run button, and nothing happens, or it fails, or it blows up, or there's a traceback. It happens all the time. One of the reasons for this is we are software engineers. Our job is to take shortcuts. Our job is to do things quickly. You don't sit down when given a program and spend 3 days writing a perfect proof of the program, making sure it's actually correct, and then implementing it once. If you're like me, you sit down and go, and just put it out in about 2 minutes, run it, it fails, go, it didn't work, and then you keep fixing it and doing it again and again and again, till finally it kind of works. We're practical, that's how engineers work. Our job is to take problems and ship things. My job is not to sit in a room all day and just think for like 3 weeks ago, you know, I got the perfect solution for that one problem. It's like, but Andrew, there's 95 other problems you haven't done in 3 weeks. Oh, I know. And that's kind of the problem. And it's our job to balance that with risk. When is it safe to take a shortcut and then take the accompanying risk? You have to always think about this. One of the nice things about being a web developer, most of my code, at least it used to, not matter too much. Like, oh, the picture might come out slightly missized, there might be a slight rendering error, it's not going to hurt anyone. That's changed slightly when I joined Eventbrite. In the first couple of years of Eventbrite, I rewrote the code that calculates ticket prices and ticket fees on all the events. And so now that code processes around $1 billion every month. If that code is off by 1%, it costs the company it's like $10 million, which is quite a bit more than I can afford to pay them in, oh, I'm sorry, it cost you $10 million, we'll try and fix it, I promise. And that's not true of just that. Like, every part of a big system has its consequences. Eventbrite has a really good trust and safety team who try and find bad events, things that are, you know, doing maybe scams or exploiting people and take them down. If we fail in that particular part of our job, people lose money, or even worse, they may, you know, have personal issues. So all these factors have to play into your mind when you're working on a big system. And you've got to remember, like, engineers in general work on these kind of things. It is the job of an engineer to make a thing that people's lives depend on. Like, these are 3 examples. Like, a traffic engineer makes traffic lights. If those don't work, you're going to be in for a bad time. It's, you know, the traffic here in Medellin is maybe already pretty bad. But even in, you know, other countries, like, if there's 2 green lights, someone's going to crash into each other. People who build bridges, like, that's pretty important. If the bridge fails, it's going to be really bad. Let's not talk about the fact that half of the bridges in the US are about to fail, but that's a different problem for engineering. Planes is my favorite example. Imagine how ridiculous planes are. Aircraft literally fly through the sky at 800 or 900 kilometers per hour, and they are the safest thing basically on the planet. You are more at risk driving to the airport than you are once you get in the plane. Think about that for a second. Like, you're in a normal car on the road, the car can stop. The car can pull over and just go, you know, the engine's stopped, we're going to pull over and call for help. The plane can't do that. Planes can't stop and wait. That's not part of how they work. If they stop, they go this way. And so, like, the planes have to be so reliable, yet we've taken such a complex issue. There's so many moving parts in that plane, yet it keeps flying. It's super reliable. How does that work? And particularly, how can we kind of approach that as software engineers? Let's also bear in mind that all of these things now run on software. When the Golden Gate Bridge was designed, it was designed by hand on paper. These days, bridges are designed using software. You make the bridge on a computer, you say, okay, let's pretend 25 cars driving across it. It goes, okay, the bridge is going to fail at that point, you fix it, and then the computer tells you you're okay. If that computer program is wrong, the bridge will collapse later on. Let's not even talk about the Boeing 737 MAX. I'm sure you've heard about that. Like, software and aircraft is never a great combination these days. One of the differences here is, in software, we have this amazing thing that it's cheap, it's fast. We can take a program, we can run it quickly, we can run unit tests, we can break it down. When I talked to mechanical engineers at university, they spent 2 weeks making one thing. The idea of unit tests, the idea of testing something that quickly, filled them with a mixture of envy and anger, right? Like, you can do what? How quickly? Like, 10,000 tests in a minute? What? Like, it's just not possible in other forms of engineering. We have this amazing advantage where we can not only just sit down with a laptop, and, like, laptops are expensive, but, you know, $300 or $400 US gets you a pretty decent laptop to write code on. And with that, you can go and write basically anything. You try buying the equipment to even make a simple, like, piece of mechanical equipment. Trust me, I've tried. My garage is not big enough. It's expensive. Like, even a basic mill or lathe costs you thousands and thousands of US. And so we have this real advantage. The problem is, as engineers, we have maybe taken too much of the fast and run with it part of it, and not enough of the, it's kind of risky. And this is kind of because the real world is a pretty nasty place. Nastier than you might think. It's not only like we'll ignore politics, we'll ignore climate change, there's many bad things in the world. Just the actual physical universe is not quite as nice as you would want it to be. So I have 3 questions for you that I'll give you answers to in a second. These are common questions I pose to people when I'm talking about computer reliability. How often does a cosmic ray from space or a supernova or the sun affect RAM? And flip one of the bits in RAM so you've corrupted some data. How long, if I take an SSD and leave it on a shelf, can it keep data? And when or how often does quantum tunneling, which is literally a quantum effect of electrons vanishing and going through material by themselves, affect CPUs? They're all not quite what you think. The first one is 36 hours. Every 36 hours, a bit in your computer is flipped by a cosmic ray. It is way, way more common than you think it is. Like this laptop, in the time since I wrote this talk, has had 4 or 5 different bits flipped somewhere in it. Now, I've got to hope those bits are not in the talk slides, otherwise it's going to go very wrong very quickly. But it's really common. In fact, the research for this comes from research by Boeing when they're researching the number of errors that happened in their aircraft on the ground. They're like, oh, it turns out that there's so many bits in a computer, there's so many cosmic rays, and they happen more often than you think, that one of them is going to get flipped. Now, this is fine if it's like a picture or if it's something boring. If this is your bank account, and like your bank's computer loads your bank account into memory, and then just before it reads it, a cosmic ray comes in and flips the 1 to a 0, they go, oh, you've got no money anymore. Like, that's the thing you've got to prevent, right? Thankfully, we have what's called ECC RAM, error checking RAM, which finds and fixes these kind of things. But most of your laptops do not have that RAM. It's more expensive. And so most of you, without even knowing it, in the last couple of days, have had some small piece of memory corrupted by a cosmic ray. Let's just hope it wasn't important, eh? SSDs on a shelf, they last 3 weeks to a year. Never use SSDs for backup. Now, SSDs, if you're not aware, the modern solid-state hard drives, they trap electrons in a kind of like a weird quantum cell, which and like the charge level is how much the data is. It's amazing science. It's fantastic. The read speeds and write speeds are great, and the trade-off is they just don't last very long without power. Enterprise-level SSDs, the ones you find in servers, they only last 3 weeks. Ones in like this laptop I have here, this is like a normal consumer one, that will last more like a year. But of course, this gets worse as it gets hotter. If you have an SSD in 50 degrees Celsius, it will last about a day. Like the heat energy makes those electrons decay much faster. And so I've seen people going like, it's great, I have cheap SSDs, I use them for backup and put them in a big storage box. I'm like, what are you doing? Like you're gonna go back in 2 years, they're all gonna be basically corrupted. Like the bits gonna be flipped everywhere. So you've got to think of this kind of stuff. Ironically, hard drives, the good old spinning metal kind, they last for much, much longer. And so if you're doing backup, you still want hard drives for that reason. Quantum tunneling, by the way, is a continuous effect. Modern CPUs just deal with quantum tunneling all the time. At some point, CPUs got so small, engineers were like, that's weird, there's like current leaking to the wrong side of the transistors, what's going on? And they found out that quantum tunneling was just happening continuously. Thankfully, we can mostly ignore it. It mostly is just extra heat energy or like the wrong kind of charge. As long as it's not too small, we can deal with it. But like, if you are designing CPUs these days, quantum tunneling is a very active part of your job, which people don't seem to appreciate very much. And what I want to underline here is that like, this is just some of the things that go wrong, right? There's many, many more things than this, but you have to always be prepared for that kind of failure. Like, you have to design for the cosmic ray hitting your computer, for something going wrong. My favorite example that I love using in interviews or with new engineers and sort of mentoring them is networking. Now, people often assume, okay, the network is either up or the network is down, which is already a bad assumption because like, the real world is not that simple. The real world is the network is gonna be like up and then 10 seconds slow and then 1 second and some reason it'll go via Australia and then it'll come back again and eventually it'll be the right speed but everything will be in the wrong order. And like when you describe this, people are like, wait, networks can not be up or down, they can be slow. This is a common problem. And so you have to design not just for simple failure, like the network being down, but for complex failure. Like, well, the network is up, but it's 4 seconds to the next server, and it's dropping half my packets. What do I do? Like, a very stupid, dumb program would simply go, well, the network's up, this thing says it's definitely up, I'm gonna keep sending things, and it would probably crash. And so if you design for failure and design for the worst case, when these things don't happen, you'll be very happy and go and have a lovely coffee. When they do happen, you can be like, oh, well, it's bad, but it's designed for it. There's an idea called crash-first software, where you build software that's designed to, like, if you just turn off the computer, it's perfectly fine. The reasoning being, if it can survive that, then it can survive being shut down normally. Like, the worst thing that's happened is, like, you'll lose power all of a sudden. Like, it happened at my house last weekend. We lost power for 3 hours, but everything was fine because it's designed to deal with that kind of thing. And this kind of ties into how we think about software. Now, again, when you are taught programming, you're taught this wonderful idea of, like, you have a nice file of lines. The computer goes from the top of the file to the bottom of the file. It's very simple. Like, it runs each line in order. It's easy to think about. There's a problem, you can work out what line it's on and work that all out. Now, that's great. That is how basic programs used to work. If you go and write BASIC, that's fantastic. And even simple Python, it works great. But there's a sort of a mountain to go over of, like, from there to the real world. If you write code like this, you know, some basic asynchronous Python, Python does not guarantee those two functions will run in order. I wanted to disable the alarm first and open the door. There's no guarantee of that at all. It might just run open door first, wait 5 seconds, run disable the alarm. It might not run either of them. It might run them exactly at the same time in a weird race condition way. And this means that, if you think about just this one example, modern programs are incredibly complicated. Think of just the most basic big program you've written. Think of just like what Django is, right? Django is quite a simple framework in some respects, but it's ridiculously complicated. It has so many moving parts. No one Django core developer understands how the whole thing works. Like, I know some pieces, like Russ knows some pieces and so on, but like, we often have to ask each other, well, I don't know how that thing works, who does? And we sort of work out, oh, well, I think this person knows about that. We go and ask them, oh, do you know about this? And they're like, yes, I know about this, please ask me questions. Some people don't want to know about things, but they're the last person left. And then there are a few areas where no one knows about it anymore. For example, doing the Django async views work. All the code I was changing was written about 9 or 10 years ago. Like, literally comments in there from like, 9 years ago, Jacob wrote this. And I asked him, he's like, I've forgotten that. I forgot that like 6 years ago. Like, I have no idea what this does at all. And so I'm just going through there, like, I'm the only person now who knows how half that stuff works, basically, because I've been through it recently. Like, that's part of software. I often jokingly call it software archaeology. Your job is to go through old software and try and work, well, what was this person trying to do? Was this a ritual? Like, what was happening here? And eventually you work it out. And that's kind of part of being a lead programmer too, is like, everyone always forgets software, you've got to keep going. Now, Django itself has about 250,000 lines of code. That seems like quite a lot, and trust me, it's quite a lot when you're trying to check it out over a hotel network here in Medellin. But it's, you know, it's not too bad. You can still think about it. I kind of know where everything is. If you asked me where a particular piece of Django was, I'd kind of know roughly where to look, and probably know about 10% of how it worked. Async is only an extra few thousand lines of code too, which is kind of why I'm happy about it. Like, it could have been, you know, taking half this code and rewriting it, but we sort of squeezed it in so it wasn't too bad. But let's compare that with like actual real-world engineering. The largest passenger plane in the world is the 2-floor Airbus A380. I love the A380, it's a great plane. It's ridiculous to go into a plane and see how big that thing is. It's like, you see it next to a normal plane, it's like a tiny toy, it's fun. But it has 4 million individual parts, like rivets, screws, computer chips, panels, what have you, hydraulic aviators. That seems like a lot of pieces, right? Like somebody, well, not one person, again, a group of engineers spent 10, 20 years carefully designing every part of their aircraft. I bet if you ask them, do you know about how like the toilets work? Oh, no, like Bill, he's the toilet guy. He knows how the toilets work. I just know how like the lights work. Like that's kind of how these jobs are done. And that seems like a lot. And then you go to big software, like how software works in the modern world. You think a plane is complicated? A modern car has 100 million lines of code in it. A normal car, just like a normal car you can buy from anywhere. Like, we have so much software now just in a normal car. it's this complicated, let alone what a plane is. Like any big piece of software on the internet has a few million lines, like Eventbrite has a few million lines of code, right? No one can understand that much. Not only, this is 100 million lines of code, it runs on 100 different chips. Can you imagine trying to debug that? How do you even start? Well, what's the traceback look like? Is it 3 miles long? How does that work? Oh. And so you run into this problem of software is changing the world. As software engineers, we are basically shaping the modern world. We dictate what happens. But we have this problem that we just can't understand it. When you start out programming, at least I did, I felt powerful. I was I am like a god, right? I can control this. I understand the whole program. I understand exactly how every single piece of it works. And for me, the difficult part was going from that to a big project. Going from a junior to a senior engineer, for me, was mostly learning to let go and not be able to understand everything anymore. Because you just can't do it. You have to learn to just let that piece go. It's how do you do that? Especially if you're still earlier on in your career, I haven't done this yet. How do you handle letting go and forgetting about pieces? And the way I approach it, at least, is a handy 3-step process: abstract, verify, and forget. Now, what do I mean by that? So I think you already all do this and don't realize it, but basically it is, first of all, you abstract something. You take a problem, and either you write it yourself, you give it to a team, but you define a contract. You say, okay, this Python module will take in an image and return me its primary color. How it does that, I don't care about it. All I care about is that it takes in an image and gives me the biggest color in that image. That's your contract. You set that and you trust in it. And to make sure you can trust in it, you verify. You write tests. You say, okay, here are 100 images. We've verified these are the right background colors for them. We test the module. We make sure it does the right thing. And once you've got this, you can then forget about it. You can say, okay, I have a contract, and the contract is simple. I can understand and keep the contract in my mind at all times. Oh, this module, I give it an event, and it returns me how much it costs in fees and taxes. I can understand that. I can verify it, because I know not only their tests, but in the case of Eventbrite, there's a whole team who just work on that particular, down in Mendoza in Argentina, there's a whole team just work on the pricing system. I trust them, they know what they're doing, they've got good tests. And so I wrote it, I've forgotten about it. People come to me at work and go, Andrew, we have a problem with the pricing system. I wrote that 4 years ago. I have no idea how it works anymore, because I gave it off to a team, I trusted them, and I've forgotten about it. I have moved to other things. You have to learn to forget. That's kind of the key part of being a senior or lead software engineer. You have to trust in that ability to take a problem, fix it, and maybe trust in yourself, maybe trust in somebody else, but to just forget about it and make sure that it does the right thing. And occasionally you'll be we found a bug in it, and you're going to go and remember it all and relearn it again. But that's kind of part of the job. And this kind of underlines a key part of when I talk about engineering, people think software engineering is programming. That is wrong. In my opinion, the #1 skill you can have as a software engineer is communication. Any system you are building that is big enough to affect a lot of people is probably bigger than just you. And at that point, communication is the #1 skill. So many people don't do things like contracts or tests. They don't know what other teams are doing in their company. You've got to understand how to split problems out and how to trust other teams with problems, and then make sure that you're talking with them and making sure that your trust is good and their trust in you is good. That's part of the job. Most of my time at work is not writing code. It's going and saying, you should go and talk to this person, and you should talk to this person, and also and just basically coordinating people. That's my job now. That's still engineering. My job is making sure everyone's thinking about things right, architecting things the right way, splitting them the right way, but it's not just about writing code. The wonderful computer scientist Grace Hopper, I love this particular quote, a ship in port is safe, but that's not what ships are built for. And that's kind of the difference between computer science and engineering. And Grace Hopper was both. She was a fantastic computer scientist and a fantastic software engineer. And you've got to kind of straddle those two lines, right? Computer science is all about doing things perfectly and validating them and performing well. Computer Computer engineering is about the real world and making them quickly and dirty and testing them and getting there eventually. And you've got to kind of expect both of them. And one of the things you've got to do is you've got to build to expect growth, right? And I don't mean growth and scaling. I don't mean traffic. I don't mean users. I mean code base and code size growth. When you write software, at least when I write software now, I already immediately put things into modules. I'm like, okay, this is where the tests go, this is where my image processing goes, this is where this goes. Because I'm not planning even to have a team on this. I'm planning that I know that I will forget some of it at some point. I'm planning for my future self. I'm planning to forget. I'm planning to scale up my knowledge of the system. That's kind of what you could go into these problems doing. But you've also, as I said earlier, you've got to build to expect failure. You've got to understand that something is going to go wrong. In the world of computer science especially, like, there are parts of computer science that do model and handle failure. They're incredible. They take it as part of the theory, they work it in, and you can build perfect programs that account for failure. But it takes a long time. And there's a balance there between that and the real world. So your job is to work out, like, what are your most likely failures? What is your risks, your attack vectors if it's a security problem, right? Is it power outages? Is it natural disasters? For example, like, if all your data is stored in a single location, and that location is, say, San Francisco, California, congratulations, it's one of the biggest earthquake zones in the world. I'm sure it's very safe forever. Definitely not going to go wrong there. You have to kind of understand those threat models. There are some places in the world that are chosen for backup locations because they're very, very boring. There's nothing there. Like, well, there's no cities, there's no earthquakes, there's no volcanoes, it's far away from the sea. Like, it would take a disaster of epic proportions to affect this. And that's kind of part of their thinking. But it's more than just that. Like, even in normal cases, like, power outages is the #1 thing. Network is the second thing. Think of those at least. But also know that you can build near-perfect software. You can build software that acts basically, to a level of perfection that no human would ever notice the difference. All of you can do this, given enough time. The thing about software engineering is, given enough time, you can do anything. You can learn, you can improve your skills, you can understand how to build things perfectly. The problem is, should you, right? Like, you've got to know when not to do that. Like, when do you take the time, sit down, do the 3 hours of work, and write the tests, or write the proof, or reason about it, or find the right algorithm? Or when do you just go, and just stick it out and code it quickly? You've got to know when to balance these two things. One of the reasons I love Python, and I'm still doing Python after 15 years, is it lets you do both. Python is an incredible language for doing both of these particular problems. And it's even got better at that over time. Like, when Python was young, it was much more of a quick, dirty scripting language of like, oh, we want to replace Perl, basically. Over time, as big companies have grown up and used Python, they've affected it and added these things that make it much more useful for real work and making programs that run well. 3 examples here: types, async, and speed. And this is kind of how I think you should approach these particular problems in Python. First of all, typing in Python. Typing in Python is strong but dynamic, right? Variables don't have fixed types, except you can now with MyPy. And what the nice thing here is, you can start your code quickly, you can make a prototype. Python's amazing at prototypes. Like, you try writing a quick thing in Rust, it'll take you like 3 days. Like, oh, the types are wrong still. Oh, we're gonna go do this. Oh, the async call is wrong. Like, Python will happily ignore most of your problems. It kind of knows, but it will ignore them and let you run it mostly anyway. And then later on, you can go in and add types where you need them. You go, well, okay, in the login code, in the security code, in the money code, there we're gonna add types and tests more, and then we're gonna not have them everywhere else. And you can choose where to put your effort where it's used best. And Python's really good at that. And like, MyPy as a typing solution really comes along with that, because there's nothing better for finding out if you can do a thing than writing a prototype. But too many prototypes make it to production because the cost of rewriting one is very, very high. The ability to take a thing and then add types and add things gradually is super, super amazing. Asynchronous code. People come to me and go, Andrew, I want to write everything async. Where do I start? I'm like, first, don't write everything async. It's a terrible idea. Don't do it. I don't do it because it's very confusing. if you've ever tried to write asynchronous code, you were quickly into a giant like piece of paper with like lines, like some kind of mad like diagram, like red string, like what goes over here. It's very, very complicated. What you should do is make it work synchronously first, and then work out what would benefit from async. Like, oh, here we're calling 4 websites at once. Well, those we can simplify and do them in parallel. Here we are doing an algorithm that we parallelize. Great, the algorithm we can parallelize it and like add it progressively. Don't just start out writing everything in async. The same with WebSockets, with channels. People are like, oh, Andrew, I don't have my whole site running on WebSockets. It's a terrible idea. Don't do that either. WebSockets are really hard to understand. You've got to reconnect them. There's bytes. There's weird transports. I told them, first, write your site using polling, make it work reliably, then come back and do sockets. Because you've solved most of the problems that way, and you've got there much faster. And finally, speed. Everyone has probably heard about this, but like, don't write the fast code first. Like, the first piece of code you write should be understandable. Because again, you're going to forget about it, if you want to or not. You're going to come back in 3 years and go, well, this 7-line list comprehension is certainly totally impossible to read. I could have done it as like, write 4 loops if you can. Like, my personal rule is, if a list comprehension is more than 2 lines, it should be a for loop. Like, don't do that. It's a bad idea. You can. Doesn't mean it's a good idea, but you can do it. But don't. Just make it. Like, I often do like basic if statements. Like, I put return none at the end of functions just to make it clear. Like, I know that Python functions return none by default, but like for a junior programmer, they may not realize that. It's there to kind of remind me and make sure that everyone understands. It's like, I like code where like you can open a file of code and go, I know what this does. I can read through it. This also means like not putting things in weird modules. Like don't use multiple inheritance. Don't use mix-ins. Like if you ever try to debug a mix-in, you're like, well, the mix-in goes to here, and the other mix-in goes to here, and you've got like 25 classes later, you're working out the method resolution order. Like, it's much easier. Like, try and optimize for your, you debugging in the future is what I try and encourage. And this is kind of the balance, right? Like, scientists are amazing people. Their job is to observe and question, right? Like, science is mostly about theory and asking why and how can we do this. Computer scientists especially, like right now, there's computer scientists around the world working on some incredible problems that will affect you in about 15 to 20 years. Like they're doing amazing research into type systems, into algorithms, into P equals NP, into proofs, into all sorts of other things I don't even know about. AI is where obviously, like machine learning is where these two meet very strongly. And it's an amazing piece, and a lot of their work is fantastically important, and it's about analyzing. Engineers are much more practical. Like engineers take problems, they build solutions, they invent the solutions. Like I bet you that every single large project ever has someone who's gone, I will just hammer it in. They just got a giant hammer and just hammered it in the rest of the way. Like if you've ever seen an aircraft with what they call speed tape, which is just basically special aircraft-approved tape that you put on engines to make sure they work fine. It looks really hacky, but it's perfectly fine. That stuff's rated for like a good 20 or 30 flights. It's a case of understanding when to do things a quick way and when to do things the slow way and the correct way. Part of this is like all software we write has consequences. You may not think about it, like, you're probably not writing software for self-driving cars, or that does money transactions, or that handles people's, government taxes or whatever. But everything you write does affect someone. Like, if you're writing a social network, you affect people's mood. If you're writing things like photo sharing, you could have, like, private photos leaked, that kind of stuff. All software you write has a consequence. Please just think about, take a moment and think about, okay, what are the risks here? If this fails, how could it fail, and who would it affect? There are places where you can just ignore it and be fine, and there are places where if this screws up, someone's life is going to be affected. That's where you should take the time. That's where you should put the work in and make sure that you've got tests, you've got the proofs, you've got the contracts in place. Basically, be both these people. Like, I learned a lot from my computer science degree. I don't use it very much. People often joke and ask, oh, how often do you use your degree? I'm like, once every 3 months. Right? It's not very common, but when I need it, it's very, very useful. The ability to dive in and understand just how the big algorithm works and to analyze a piece of code and break it apart and just understand what's going on in there is super important. You have to understand when to be that person and when to be the person with the hammer. right? When people person like, oh, it'll be fine. Like, we just need to fix the site quickly and just hammer it in. Like, what I implore you to do is like, just understand those two things. Like, Python is one of the best languages in the world to do both of these in. It gives you so many options. We have so many different things. We have machine learning. We have web software. We have types. We don't have types, right? Async or sync. Like, you have all these choices. Just make sure you use all of them and know when to use them. And that's kind of all I ask of you. Gracias.